Okay, so today we start on the alkene. What's alkene? Alkene is actually a hydrocarbon and it is unsaturated hydrocarbon. So when you're asked what is unsaturated hydrocarbon, you must explain both the word unsaturated and hydrocarbon. Hydrocarbon means it contains carbon and hydrogen only. Unsaturated means they must have at least one carbon-carbon double bond. So when I ask you what is unsaturated hydrocarbon, means that it is a molecule that contains hydrogen and carbon only with at least one carbon-carbon double bond. All right. Let me just write a short one here. In case they ask you to explain both together, but you can explain separately also can. Alkenes are molecules are unsaturated hydrocarbon because they contains only hydrogen and carbon atoms and they have at least one carbon-carbon double bond. All right. So this is the full definition. If they ask you what is unsaturated hydrocarbon, defining both words. Okay. Yeah. So two parts. Okay. Only hydrogen, carbon atoms, and at least one carbon-carbon double bond. Okay. Use can. Sometimes you know, when they ask question, they ask like that one. I'll show you how they ask. They may ask like this. Everything is normal print except the word unsaturated, which is italic. Okay, what is meant by unsaturated? Then don't need to explain hydrocarbon. They claim that alkenes are unsaturated hydrocarbon. Explain why is it unsaturated. Then you just explain they have carbon-carbon double bond. That's why it's unsaturated. If they ask you to explain both, or they never emphasize explain only one, then you better explain both. Why are they unsaturated hydrocarbon? Because they're hydrocarbon, because they contain only carbon and hydrogen atoms, and they have at least one carbon-carbon double bond. The word carbon-carbon is very important because double bond between carbon and oxygen is not considered unsaturated. Double bond between carbon and something else is always not unsaturated. It's only between carbon to carbon. All right? So it looks like this. I highlight this to show you. These are the functional group, carbon-carbon double bond. Now, definition here, they say that at least one carbon double bond. Yes, at least one. They may have more because other unsaturated may have more double bond. Later, you learn something called polyunsaturated. Poly means many double bond. Okay, so there's only one. Now, remember when you write alkene, it's only one. And must have at least two carbon to start with for alkene, because if it's single carbon like methane, if you think there's a methane, then something is wrong because methane has one carbon. If one carbon, how do you have carbon-carbon double bond? You cannot achieve this if there's only one carbon. Okay. All right. Now, common mistakes in drawing the structural formula is, if you look carefully, people may draw some carbon with 3 hydrogen, some with 5 hydrogen. They're all mistakes. So you must always count the hydrogen around the carbons. For example, in this case, if you look at this carbon in the center, they count for you already. See, there's a 1, 2, 3, 4, 5. There are 5 of them, so it's wrong. In fact, the number of hydrogen is wrong. 2, 4, 6, 2, 4, 6, 7. The formula becomes like this, becomes C3H7, and this one, how can it be 7? Because the formula for alkene is CnH2n. So in other words, it must be C3H6. So obviously this is correct. Okay, if you draw too many, it actually means that your molecular formula is actually wrong. Cannot even fit already. So if the molecular formula is correct, so this is wrong, this is correct. If your CnH2n is C3H6, then I will have drawn only 6. And then I will have drawn this. I won't have extra here or here. It will fit in. Okay? So remember, always check against the molecular formula. All right, so let's talk about physical property. It's exactly same as the alkane. So I'm going to copy this thing down. Is there something here? Down the series. Oh, they do have. Okay, I'm going to highlight on these two things. Melting boiling point, insolubility, and so on. And of course, the trend is the same. I'm going to bring this trend down. This is exactly the same. Okay, let me bring it down to the alkene. So remember the physical property I highlight for you here. Low melting boiling point, which is the first one, which just how I say. I bring it down. Second one is, of course, insoluble in water. What did they say? Here you are. Insoluble in water, soluble in organic solvent. So these two are the important general physical property. And the trend now. Let me bring the trend now. This is what we have on top. See that it's the same. Melting boiling point, I give another color. Melting boiling point increases down. Exactly what I write inside here, increases down. Why? Because the intermolecular force increases as the molecular size increase. So as the molecular size increase, intermolecular force increase, therefore more energy is needed to overcome. Explanation is here. So explanation is memorize one, it can apply for all organic compound. In fact, alkane, alcohol, acid, they're all similar property like that. It's always increased down because of larger molecular size, greater intermolecular force, more energy needed to overcome. Same. So first point already. So left viscosity and flammability. So down here, it flow less easily. Increase viscosity increase. Why? Because as the size increase, the mass increase, intermolecular force also increase. Therefore, it's not easy to flow. Intermolecular force means attractive force. So when two molecules are more attracted to each other, the ability to flow slide past one another will be lesser, slower. Okay, when the molecular size increase, sometimes use molecular mass, sometimes molecular size, they are actually similar. You can always mention both. As the molecular mass increase, the molecular size increase, intermolecular force increase, therefore become stronger. Okay, so viscosity increases down. And flammability, like I say, it's not the important point here, but you may want to know is that the larger molecular size, you need more oxygen to burn, right? More oxygen. Yeah, because when size increase, there are more oxygens per mole you need to burn. So that's why less flammable. Okay. All right, here. Now kind of property already, physical property. Here is, let me see, where is it? Okay, here. First 3 points. These are all one, and below is the others. So the first one is called combustion. Let me write the word combustion here for you. Combustion, which I wrote for you for the alkane also. Okay, bigger. Combustion. Okay? Combustion. And the other one is called addition reaction. It's no longer a substitution, but addition reactions. It's all here below. Okay? All this below, 4 onward, all the way until here is addition reaction. So let me just draw the line to join together. All the way, until here. Okay? So you realize 1, 2, 3 is combustion, but 1, 2, 3, but very short. 4 and 5. 5 has A, B, C, D. All these are addition reaction. So in simple, I just visually show you that they are two kind of reaction. One is combustion, one is addition reaction. So when I teach you the next family, the alcohol family, it's also two reaction basically, combustion and oxidation. You'll learn it later. Okay, the first reaction is same for all three family. Second reaction all different for the three family. It's okay? Right, let's go through combustion very quickly. Combustion, there is a complete and incomplete combustion similarly. So when there's a complete combustion, you always produce only two things, carbon dioxide and water. To make life simple, excess oxygen to form carbon dioxide and water. And down here, we did mention about percentage by mass. I think we did a calculation before. So alkene usually burn with smokier flame and sootier flame. Why? Because they have a higher percentage by mass of carbon compared to alkenes. All right. Oops, sorry. I think it's 1 and 2, not 3. My eyes a bit not clear. Sorry, I just make it a bit up a bit. Yeah. So sorry for that. Addition reaction is 3 onward, not 2. Okay. So sootier flame, because higher percentage by mass of carbon, which you need to know how to calculate. I think I did before here. This is the one. Repeat, ethane, ethene. Must compare same number of carbon for both, to be fair. Percentage by mass of carbon in ethane equal to the mass of carbon over total mass times 100, 80%. Ethene, total mass of carbon divided total mass of ethene times 100, 85.7%. So we can conclude that ethene has higher percentage by mass of carbon of 85.7% compared to ethane, which is 80%. Therefore, you burn with smokier and sootier flame. All right, so this one, I'll bring it down and put it beside the here. Okay, there you are. Okay, my text didn't come down. Okay, so the explanation is here. I think I sent to you last week already. If you look at the chat last week, you have it there. Okay, I mean, if you use, I'm not sure how you use iPad. If you can cut and paste, put it beside the notes, that'd be also fantastic. Okay, so now I'm going to move on. Is it okay to move on to the next part? I'll go through until bromination. May I give you a short break after that? Let me go through one set first, one additional reaction, then we'll let you short break. Okay, So now we come to the addition reaction, which is the most commonly tested, and I'm sure that your teacher will test you this. Most commonly tested organic chemistry question. So you must know that alkenes undergo addition reaction. The reason because they contain carbon-carbon double bond. Okay, addition reaction can also occur to carbon-carbon triple bond. As long as it's not saturated, I can have addition reaction. So double bond, triple bond, or carbon also can have addition reaction. Possible. All right, but in a syllabus study carbon double bond only. So look at this. I have a carbon-carbon double bond. When I break the double bond up, I break one of the bond in the double bond. I assume I break the below one. Then I'll form two single bond, which I can attach two atoms, two molecules, atoms out here. I can be a single atom like bromine, can be H and OH. May not be a single atom, can be OH even. All right. So atoms of reactant can be added across the double bond to form a single saturated product. So it was unsaturated with double bond. Once you break one of the double bond to form two single bonds, you can add atoms across these two single bonds to form a saturated compound. Okay, so what's A and B? A and B has three possibilities in the syllabus. A and B can represent, in this first case, is bromine and bromine. So you get bromine and bromine added here. The next case is actually hydrogen and hydrogen. We add two hydrogen across here, means H and H. Possible, right? Or you can have a H2O. H2O, you split. Okay, let me just write it below here. So Br and Br can be like that, one by one. H and H can be here. What I mean is that A and B can be Br, can be H and H, or can be H and OH. So I can substitute my AB to become Br, substitute to become HH, or H and OH. So these are the three reactions you study. So let's look at the first one, bromination. Bromination actually is addition of bromine. Take note, liquid bromine, not aqueous liquid. So they react at room temperature. So when alkene is a gas. Alkene, this small molecule is a gas. So therefore alkenes are bubbled because it's a gas. Okay, at least first three member, ethene, methane, propene, butene, they're all gases. I write for you. Ethene, propene, and butene are gases. So if you use them to react with bromine, you say they bubble through the solution. First four member, that means up to butene or butane, they're all gases. Okay, the rest you don't have to worry because somewhere around the 5th or 6th or 7th, they'll change to liquid already. So they bubble through the liquid bromine. The red-brown solution decolorize. Bromine is red-brown. It decolorize or it turn colorless. So in this case, I will say this colorless. Here, this is colorless gas. Red-brown liquid. Okay, I must be very specific in case students ask me what are they gas or liquid? This is a gas. Yeah, so horrible. Okay, let me just put it this way. I can't stand it. The app is crap. Okay, never mind. Colorless gas, red brown liquid, and this is color solution. Okay, equals color solution. So colorless bubble in the red brown liquid, turn the entire liquid into color solution. Okay. Now, do you need to know the name? Of course, as pure chem student, the best is you write chemical name. It should be like that. Okay, this name has significance. The 1, 2 refers to the carbon position. Carbon 1, carbon 2. Carbon position. They attach a bromine. Di means 2. 2 bromo. 2 bromo means 2 bromine. And then this is the alkane because no more double bond. From ethene become ethane. Do you see that? My ethene has converted to ethane. Okay. Now I show you another one, a possibility like this. 1, 2 dash dibromo ethene. Now what is this molecule look like? This is not exactly same as the dibromo ethane, but because it's ethene, so I must have double bond. Okay. Wait, sorry. I'll do this like that better. Oh. You see that? 1, 2 dibromo ethene. Ethene means there's still a double bond. Ethane means no more double bond. Okay, but it's not in your syllabus, but I just want to show you that there's a possibility of you see an ethane. So if you think there's ethane, it becomes like that. If you write wrongly, of course, it's wrong. So the product of addition is always an alkane because alkane means no double bond. Is it okay? Any question? So what's the condition? What's the condition for this? No condition. This is a rapid reaction without special condition. Rapid reaction without a special condition. Okay. Unlike the substitution requires UV. Unlike substitution, okay, in alkane, right? Which requires UV light. Okay, that's it. So I hope you're clear here. The difference between addition and substitution is substitution requires UV light. Addition of bromine do not require any condition. It happens just you shake it together, it's done. The only reaction now here in addition, there's no condition. The rest of addition got some condition one. Okay, so try to memorize this. I don't want to go on further yet. I'm going to give you a 5-minute break. Yeah, after come back, quickly memorize this. Okay, memorize what they become and learn how to write this equation. Just substitute, just add 2 more bromine to it. Let's have a 5-minute break, shall we? Okay, so the first reaction we learned down here in addition reaction of alkene using ethene as an example. It can be ethene, propene, butene, all possible. The only thing you need to take note is where is the carbon-carbon double bond, because addition reaction occurs across double bond, just like this. Double bond will turn to single bond and then add the two atoms inside there, or could be a group of atoms. So bromine is added across the double bond, and this thing decolorized because bromine is red-brown. Remember, not red, not brown, but red-brown. And it turns to colorless because this dibromo, 1,2-dibromo ethane is colorless solution. Okay, that colors compound actually, right? So remember, it's ethane, not ethene. If I show you the ethene, must have a carbon and double bond. And then this reaction now here, just remember bromination. Sometimes they call it halogenation. I write for you the word halogenation. Halogenation is another name for this bromination. You can write it down for yourself because it also can add chlorine to it. Sometimes they call it bromination, chlorination, but generally it's called halogenation. Okay. Now, next one is hydration. Hydration is adding of steam, adding next one with hydration, hydrogenation. You see that? Hydration, hydrogenation. The word itself tells you what you add. So hydration is actually water. Hydrate ma, okay, water. So addition of steam is called hydration. And the condition is 300 degrees Celsius, 60 atm at phosphoric 5 acid catalyst. Okay, three conditions. Highlight this, huh? So 300 degrees Celsius, 60 atm and phosphoric 5 acid as a catalyst. Right, so what do you do is this. You break out the double bond, form two single bond, and you add H to one side, add OH to the other side. So the only place you break is the double bond as well as the single bond in this one. So you break one double bond, you have only one single bond left. You break this bond, you have hydrogen and OH separated, H joined to one side, OH joined to the other side, and that's it, done. So this is called hydration. Okay? Hydration. Okay, give me a second. Let me just take a look. I just want to check the textbook to confirm that this condition is exactly the same. Because sometimes they have slightly different temperature or pressure. Just want to make sure that this book is aligned totally to the textbook. It should be same. Let me check. Okay. Okay. Now. Okay. Okay. Textbook will be on page 349, I think. 348. Okay. Condition is correct, exactly same. 300 degrees Celsius, 60 atm, and phosphoric 5 acid. So you can memorize that. That's exactly same as in the textbook. If you look at other books, I've seen before, previously it can be written as 65 atm. All right. 300 degree, I think it's the same. 65 atm I saw before. But remember it's a 60 atm. So memorize the condition. And how do I know it's a condition, not a reactant? Because I put it on the equation itself and on the arrow of the equation. So whatever you put on the equation itself is not a reactant. You put in front is a reactant. Put behind is a product. You put here is a catalyst. Simple enough? So how does it happen? It happened that when heated to 300 degrees Celsius at 60 atmospheric pressure, 60 atm, it means 660 times the normal atmospheric pressure under compression. And in the presence of this catalyst, this bond will be broken. And this bond will be broken. H add to here and OH add to the other one. Become like that. Okay, condition memorized properly. They may ask you 1 mark only, usually. Next one. Next one is hydration. Hydration is also have another condition. So hydrogenation, sorry. Hydration is water. Hydrogenation is addition of hydrogen. So there's a 150 degrees Celsius and nickel catalyst. All right. At 150 degrees Celsius and nickel catalyst. Again, the conditions are written on the arrow of the equation. Please memorize it. Now this time it's even easier. You break the double bond. You break the double bond. Where's my arrow? Here. And you break the single bond here, and then you form this one. So basically, I'm going to break this bond. I'm going to break this bond. And then when you form two single bond at the carbon, I'll add hydrogen to it. That's all. Condition is important. They'll ask you, Nickel catalyst 150 degrees Celsius. All right. Any question? No. This one you memorize this thing particularly well. Later we will learn about hydrogenation of margarine. Take note of this word. Hydrogenation of to produce of vegetable oil to form margarine. So this is what we're going to use as application. Okay, similar to this. Hydrogenation of vegetable oil to form margarine. So, margarine is what we eat, the soft, creamy butter kind of thing. They call it margarine. Creamy, buttery, I think spread you put on the bread. Fairly, you know what's margarine, right? Margarine is a spread that you put on the bread. It's very nice. Usually they dip it salted, I guess. So vegetable oil make it margarine. Can you imagine margarine is oil? Just oil. We're eating oil, but it tastes nice. Butter is also oil. You know butter is just oil. Yeah. It's so nice to eat. Okay, anyway. Yeah, so we are done with this. Later we'll cover more under here. Yeah. Okay, maybe we just go there and see. Is it there? Here. No, here below. At the bottom. Since we talked about that, let me see where is it. Is it below? Yeah, here. We just must cover together so that you will not get confused. This is application in case you forget already. So therefore, we just want to go to this page of the notes. Page 223. All right. Now, since we cover about hydrogenation to convert double carbon double bond to single bond, we want to convert vegetable oil, which has many carbon double bond, into a solid margarine, okay, which is much lesser carbon double bond. Take note of the special thing is that vegetable oil is a liquid. Margarine is a solid. Okay, so look at the diagram. This is just a part of the vegetable oil. This is a saturated margarine, this vegetable oil, and you realize that there are carbon double bond inside. Okay, this is only a small part of the big molecule. It could have hundreds or thousands of carbon, very big. Okay, not 100,000, maybe a few hundred or maybe a few thousand. This is called polyunsaturated. Polyunsaturated. You see the word? Poly means more than one. Okay, so maybe I write for you the little definition here. Polyunsaturated. Means it contains more than one carbon double bond. All right. I don't like this thing. Why is it always appearing? Okay. More than one. Okay. So under alkene, under ethene, propene, those things, you only have one. Just one. You don't draw one, you're wrong. But vegetable oil has more than one. So how to draw vegetable oil? You just randomly draw double bond in between, at least 2 or 3 of them in the long chain. How do you draw margarine? If you same number of carbon on both this side and this side before after reaction, same number of carbon, 6 here, you must draw 6 here. If you draw 8 on one side, you draw 8 on the other side also. I just want you to show that all are saturated. That's it. For unsaturated, turn to saturated. So the condition now here, they ask you, what's condition? Condition is there must be a nickel catalyst and 150 degree, which is a gentle heating. You know 150 is very low temperature, just above boiling point of water. Your Bunsen burner is 700-800 degree. Your candle is 500 degree. So 150 degrees just basically warm it only. So it converts some not all of the carbon double bonds into carbon single bond. Okay. So you see, margarine is more saturated and has higher molecular mass. Higher molecular mass, higher boiling point. and therefore exists as a solid. I repeat, when you convert all the carbon-carbon double bond sum to single bonds, or most of it to single bonds, you realize that the molecular mass increase. And higher molecular mass means higher melting point, means it's likely to exist as a solid than a liquid. So another point you may want to infer is that if it's the more saturated it does, is harder is the margarine. If 100% saturated, then my margarine will not be tasty anymore. It'll be harder, much harder. Maybe chewy, I don't know. Alright, so margarine you want to be very soft, okay, then you want to be partially saturated, not completely saturated. So another point you can take note is the more saturated the margarine, the harder it is. Full stop. Okay, the more saturated, the harder it is. So I guess they are not totally saturated, but maybe partially, 80% maybe saturated. Interestingly, if you oil can be quite disgusting. If you put oil, they only put oil in the mouth, quite disgusting. But this is a saturated fat and yet not disgusting. Yeah, there's some taste added to it, I guess. Maybe some sugar and some salt added inside there. I don't know how it works. But with purely solid oil, I don't think it's that tasty. But margarine is tasty. So making margarine, one of the part is saturating with hydrogen. But I'm sure there are other chemicals added to it. Not that simple. If not, how to be so tasty, right? Yeah. Do you remember how the margarine tastes like? Creamy, right? Creamy, just like butter. Okay. So this is a application. We can go back to the thing already. Okay. Here. We're done with the addition of hydrogen. Okay, so this next part is important. Here, this one. This is applicable to all kind of double bonding. So if you add hydrogen to this, carbon-carbon bond, you realize that each carbon-carbon double bond react with only one more hydrogen. Look carefully here. Every double bond need only one H2. If I have two double bond, I need two of the H2. If I have three double bonds in the molecule, three of them, I'll need 3 moles of hydrogen. So in other words, each carbon-carbon double bond reacts with one more hydrogen. So the number of more hydrogen reacted indicate the number of carbon-carbon double bond. This is the most tested. Seriously, this is the most tested kind of question, especially when applied to polyunsaturated. So if I have a vegetable oil, one more vegetable oil requires 4 more hydrogen. How many double bond are there inside per molecule? I repeat, one more vegetable oil reacts with 4 mole of hydrogen. How many double bond are there in one molecule of the vegetable oil? How many carbon double bond are there? Answer should be, sorry, 4. Trisha say 4. Feline, do you agree? One vegetable oil plus 4H2 to become saturated, totally saturated. So the ratio is 1:4. It means that vegetable oil has 4 carbon-carbon double bond each. Because every time you bond with one H2, you need to have one double bond. 2 carbon-carbon double bond needs 2 more H2. If I need 4 more H2, I must have 4 moles of carbon-carbon double bond. So the critical fact is here. Critical. Number of mole hydrogen reacted indicates the number of carbon-carbon double bonds present in the alkene. But in our alkene here, it is always 1 mole to 1 mole because alkenes in general has only 1 carbon-carbon double bond. But in the alkene, something similar to alkene, but it's not exactly the alkene, like vegetable oil, there are more than 1 carbon-carbon double bond. So how many double bond you have is how many hydrogen you need to react. And this one is a commonly tested concept. Okay. All right. Now we're going to go to a next one here. This one actually will cover more in chapter 21, two chapters later, addition polymerization. But for here, you just need to know generally what does it look like. It's so general that you don't need to know the condition, except that you just call it high temperature and high pressure, and there's a catalyst. Usual condition is usually temperature, pressure, catalyst, right? But down here is high temperature, high pressure, and need a catalyst. But what they are, don't need to know at this moment. All right. In fact, catalyst later, I think you will learn catalyst probably, but temperature, pressure, just say high because they are a variety of temperature, pressure. It may not be exactly the same. To form different kind of polymer, your temperature, pressure should be different. Okay. So now here, let's look at this. Many alkene molecules can combine to form a long chain molecule called polymer. So a polymer, the word poly means many. Mer means unit. This is unit. Units. 1 unit, 2 unit. This is many. So when many alkene join together, it's called polymer. Each alkene is called monomer. So this one is called monomer. Monomer. Okay, I'm right clear a bit. Monomer. 1 mer. This is polymer. Many mer. Okay, many mer not mixed together. Many mer join together. It's called polymer. So remember the polymer. We'll learn about definition, polymerization, polymer, all the precise definition we'll learn in chapter 21 under the chapter polymer. But here just general. Just need to know that my alkene can undergo addition polymerization to form a large molecule called polymer. And the condition will be just high temperature, pressure, catalyst. So look carefully, ethene form polyethene. The name has 2 parts. Ethene form polyethene. Right? Add the poly in front can already. So my propene will form what? You'll form a poly bracket propene. Okay, simple enough. Something new, but today you should understand. When I put the word poly in front of ethene, means I join my ethene together already. So 1 unit or 10 units joined together is called polypropene. The polyethene. If it's propene, become polypropene. Okay, if it's butene, it forms poly bracket butene. Okay, so it's very simple. You just put a poly in front. So what's the difference in the writing? The formula is this. Look at this. They draw, okay, I use the circle. They write the N in front. Means N number of ethene. N number of ethene. Join together, this N is behind. This behind means you repeat this structure. This is a repeat unit. Repeat unit. The repeat unit is draw only once. And then put the N means repeat N number of times. So this bracket is a Lego part. It shows you only one piece. But N here means this piece is repeated N number of times. So if I give you 1000 monomer of ethene, it forms one polymer with 1000 repeated parts, joined together. Take note that this is drawn beyond this. Just I told you, just like Lego. Imagine it's a Lego. On the left, it can join to another piece of itself. On the right, it joins another piece of itself. It repeats many, many times. Is it okay? Yeah. So sometimes it's drawn like that. Sometimes it's drawn like that. Sometimes they ask you to draw 3 repeat units. Dot, 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 dot. So this is 3 repeat units. Okay. Okay, so this is 3 repeat units of a polymer. Why repeat unit? Because each piece must have 2 carbon. Okay, because 2 carbon will show you what was the origin. This is show you what is original ethene. Ethene become polyethene. So this join together to form a single covalent bond join together to form polymer. Any questions so far? We'll do a much more on the drawing of this all these propene, butane. Some may wonder, you may ask yourself that propene has 3 carbon. Do I draw 3 carbon? Answer is no. You just draw 2 carbon still. You only draw the carbon-carbon double bond. The rest of carbon you put at the bottom. Let me join downward. But don't worry, it's not covered in this topic here. We'll cover in the next 2 topics, second 2 topics later. Okay? In this topic of alkene, the only thing you need to know is that what happens when alkene undergo addition polymerization. Alkene will form the polyalkene. Condition, high temperature, pressure, and catalyst. Details, no need to know yet. Okay, let's move on. Okay, ethane react with bromine to form 1,2-dibromo-ethane. Now, what is this wrong? Why does ethane react with bromine doesn't form this? Look carefully, I'm joining my 2-bromine. I'm joining my 2-bromine to the same carbon. Is it possible? If you draw both to the same carbon, then where was my double bond just now? Where is the double bond? The double bond has to be between these 2 carbon. Remember, it was like that, right? So when you break the 2 double bond, the 2 single bond is downward. They must be joined to 2 carbon side by side. So let me write a short note for you. In addition, reaction, the added atoms must be on 2 carbons side by side. Okay, write this note now. I'll explain a bit more because this is where the test question come out. I give an example like this. Okay, this is propene. Okay, I'm going to leave this intact. I'm not going to touch this. Okay, draw here. Okay, this is what I become. If I add bromine to it, where does it go to? The bromine can be attached to, okay, let me just erase this. Single bond, single bond, single bond. I can attach here. All right, it should be like this. Or it could be other possibility like this. Look at this. I can draw you another 3 possibility. 1, 2, 3. Oh, so why so slanted? Okay. Okay. Carefully what I'm doing. This is the first one I can draw. First one. Second one is this. I can draw the bromine on the side. Here. You can draw a bromine on the side. Why? It still fulfill this one. Added atom must be on 2 carbon side by side. On 2 carbon side by side. Carbon 1, carbon 2 side by side. Bromine, bromine. Yes, this is possible. How about the next situation? Can I have on top? Can I have top and bottom? Yes, right. It's still on the first carbon. This on second carbon. It still fulfill the thing. Added atoms must be on 2 carbon side by side. You must know. So 2 carbon side by side. Yes, correct. And the third situation, the last situation is like this. Oh, actually, there are much more. Then with the bromine on top, I can have this and have this also. Possible. Yeah. So let me draw a few more. Okay. All these are possibility. Okay. So I just want you to see that it's possible like that. So this is the third one. I use the green. 1, 2, 3, 4, 5, 6. You draw any of these also still correct. But you draw you draw 2 bromine on the same carbon, wrong already. Look carefully. All these are different arrangement, but they are still added to the atoms of carbon side by side. Is okay? Okay, Trisha. So if I cannot see clearly, I highlight. This is my 2 carbon. Of course, I don't do any highlight lah. These are two carbon with a double bond. Then look carefully, visually, you check. Are my two bromine added to the two carbon, one on each side? Yes, 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 and yes. All these are correct. Okay? So this is an important concept. I will send this to you. May not be exactly that neat, but once you understand and remember, then that's good enough. Please remember them. Okay. Interestingly, I mean, they can test you a lot of things. They test you this kind of things. You see, because students never realize such minor details, and then they realize they do not know. They will think that this is acceptable. Bromine on the same carbon is not acceptable. As long as two bromine added to the same carbon, not acceptable. This must be substitution reaction. I repeat, this one must be substitution reaction. Okay, let me put here. Can only be from substitution reaction. Okay? Put a note here for you. So this one can be only from substitution. I substitute 1, substitute 2. Whoever is substitute, I don't care. It's just substitution. Can? Okay, good. So this is a type of exam question that can come out for you. Then next part, I'm sure you come to one part that's very interesting is that, hey, where does my alkene come from? Alkane is crude oil. Alkene is what? Alkene is actually formed from alkane by cracking. See, manufacture of alkane, small alkane, and small alkene by cracking. The original alkane are the one that come from the ground, right? Come from the ground. So let me highlight this. So cracking is the breaking down of a large hydrocarbon molecules into smaller hydrocarbon molecules. Now, catalytic cracking is catalyst used to speed up reaction, and it's good to know temperature 600 degrees, presence of catalyst, aluminum oxide, as well as silicon dioxide. Either one. Okay, usually they come together because aluminum oxide and silicon dioxide, sand and clay, more like sand and clay kind of thing, you know. Aluminum oxide together with sand is formed a kind of clay. So a clay pot will have both of these. So aluminum oxide heater here. This is a liquid petroleum, liquid state. Liquid, implies larger molecule. So I write for you to note, you better copy this thing now. It's a liquid state. Why? It must be a larger molecule than a liquid. Here is gaseous state. And definitely gaseous are smaller molecules. So you can actually tell from the physical state, what are they? They're big and small molecules. So very simple. I put the large molecules inside this glass wool, which is not supposed to catch fire. I heat up the aluminum oxide to 600 degrees, which is typically Bunsen burner temperature. And then you heat, after that you must heat here also, you must heat it to vaporize it. Heat both parts. Make sure that this thing is hot enough first. Then you heat this into vapor, pass over. The vapor pass over will crack here. And then turn into gas and come here. So they form short chain. Take note of the word short chain. Alkane and alkenes. Now, don't need to memorize this. Just need to understand that the sum of total carbon and hydrogen on the left must equal to the sum of carbon and hydrogen on the right. So let me go through one. Listen carefully. Let's look at the first row. Look at the first row. 13 carbon here. Whatever you split up, they still must have 13 carbon. So 2 plus 3 plus 8 is 13. Simple, right? I cannot have carbon disappear in the air. It can either be the first reaction or second or third reaction. It's not fixed one. The only thing you need to know that before and after reaction, the carbon must be the same. Hydrogen 28. 28 is equal to 18 plus 6, 24 plus 4, 28. Yes, done. So look at second row. 13 can also be 2 plus 9. Wait, something's wrong. Okay, so there are 2 of them in front. So 2 times 2 is 4. 4 plus 9 is 13 because there are 2 molecules of ethene. Each molecule is 2. So 2 times 2 is 4. 4 plus 9 is 13. 2 molecule ethene. 2 times 4 is 8 hydrogen. 8 plus 20 is 28. It's correct. So it can be second one. Can we have a third one? All right. What they try to show you is this. They show you that there are, look carefully at what I'm pointing. I'm going to point this is ethene, ethene, ethane. No, alkene, alkene, alkane. See, alkene, alkene, alkane. Alkene and alkane, possible. Or alkene, 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 and hydrogen. There's no alkane, but there's hydrogen. So when there's no alkane, there could be hydrogen. So what are three products I can produce? Three products I can produce is small molecules of alkene, smaller molecule of alkane. Look at this. My alkane here on the left is 13. Can you see my arrow? 13. My alkane here is 8 only, 9 only, or 8 or 9 only. It's smaller alkane. So a large alkane turn into alkene and small alkane, or large alkane can turn into small alkene, both small, or large alkane can turn into alkenes, small one, plus hydrogen. Hydrogen is possible. Any question? So then what's so important about all this? You just need to understand. I repeat, I just need to understand that the total on the left and total on the right must be the same. So the statement number 7 says the total number of carbon hydrogen in the products is the same as total number of carbon hydrogen in the reactant. So the left and the right must be the same number. So usually how they test you is like that. They will draw you one of these. For example, they draw this one and then arrow this one. And then they leave this one blank. You do see this. They say 2x. What is x? This one plus 2x form this one. No, this one form 2x plus this. What is 2x? Obviously, you take 13 minus 9 divided by 2. Then 28 minus 20 divided by 2. I will have gotten the formula of C2H4 already. 2 units of each. Okay? You will come to this question practice very soon. Don't worry. All right. Then what's important is this one. Surprisingly, and not surprisingly, I put star here. That's what they ask you. Why you need to do cracking? Okay. In this case, they say produce petrol to supply fuel for running vehicles. But a better answer to this is what? Okay, is to produce, is to convert large molecule of large, let me write first before you copy. The answer is too short. You will not get a mark just like that. Okay, cracking, why is it used for? I say produce petrol is not the full answer. Basically, the idea is this: petrol is in high demand. Higher demand than is supply. So the only to produce more petrol is to crack larger and less useful molecules to become petrol. Let me see whether do you write that. Oh, they didn't write that. Okay, never mind. Okay, never mind. Let me just write a proper statement for you. Petrol has higher demand than is supply from crude oil. Okay. Larger molecule of alkenes are cracked. Okay. Which are of lesser demand are cracked to form petrol. Let me just write it down properly. Okay. So petrol has higher demand than is supply from the crude oil. Crude oil doesn't supply enough petrol. So larger molecules of alkane which have lesser demand are cracked to form petrol. Okay. In order to meet its higher demand. Okay, so that's the answer. You must explain that it has a higher demand than supply. So whatever I take from crude oil is not enough. So in other words, I can do fraction distillation. I can separate out the different component of the crude oil, and then I realize, hey, whatever I get for petrol component, the smaller molecule, it is not enough to meet the demand worldwide. No matter how I produce, I cannot meet the demand. But I do have a lot of alkane, the larger one, which is of lesser demand, stocking out somewhere. I couldn't use it. Not so useful, not so high demand. You realize they have a lot, so much more supply. And imagine Singapore do the fraction distillation, they realize, hey, my petrol cell until not enough, but my larger molecule, how? They don't want to put a tank and store there, right? So what they do is they crack the larger molecule into smaller petrol in order to meet its higher demand. Is it okay? So this is point number one. Because petrol is not made purely on cracking, petrol is also found in the distillation of crude oil. One of the components is called petrol. Just that it doesn't meet the demand, too high a demand, need too much. Okay, demand supply simply means that demand means you need people asking to buy. Supply means the supplier, the people who make the petroleum into petrol, the supplier, they try to supply the fuel, sell the fuel. But the seller don't have enough, so they must crack to form more to sell more. All right. Now, is it okay for you? I give you a short while. You need to copy down. Please do copy down. Let me drink. Take a drink. Mm. She here want to go and get some water. It's okay. You want to get some water? Give you a 1 minute break. Go get water. All right. Okay. So now we are at the cracking. This is a very exam popular question. So I make sure you know how to write. Okay. It depends on how much teacher want you write because some teacher even give you a longer explanation. Okay. So always listen out what are the keywords they search for. The keyword down here, which I feel that O-level emphasize on is petrol is higher demand. Okay. More than it can be supplied from the distillation of crude oil. So in order to meet higher demand, the larger alkane molecules like you don't study the name, so you do have to code the name, like bitumen, diesel, the larger molecule. If they give you a database question, they probably give you a table and then they give you the different molecular size based on number of carbon. You can just code anything that's below the bigger number. For example, petrol is about 8 carbon plus 8, 9, 10, 11, around there, 8 carbon. Okay, for petrol. You can create any larger molecule with, let's say, 20, 30, 40 carbon. Crack into 8 carbon is no problem. Okay, larger than twice the size can be cracked already. If less than twice the size, a bit difficult. I think they usually give you larger, like maybe 30 carbon. Yeah, you can crack into 8 carbon petrol. Okay, so the larger molecule because they are lesser demand. If they're high demand, of course cannot lah, because everyone fighting for the large molecule, then cannot, right? But because nobody fighting for them, you can sell them cheaply, and therefore you're gonna crack the cheap products into the more expensive one to sell. Okay, second one. Second one is alkenes. You can produce alkene. You produce alkene, which are important starting material in the petrochemical industry, like making plastic. Okay, okay, let me just put here myself. Cracking produces alkenes. Okay, which are raw material. They call raw material to make what? Plastics. You can just do petrochemical is a very general term. Plastic is one of the product of petrochemical, but of course, plastic again refers to many, many kind of plastic, but they're all made from the alkene. Alkene are raw material to make plastics. Okay. And the last one, of course, you can just write from here. This one, the last one is okay. Produce hydrogen gas they used to make ammonia, which make fertilizer, right? Yeah, this is to make fertilizer. Oil to make margarine, which people like to eat, as well as to make rocket fuel. Hydrogen is a rocket fuel, which is a very much high demand now. There was once upon a time we used hydrogen as a fuel for vehicle, but that is not so popular now. I mean, they are still using, but not so popular because they realized that hydrogen is not very available in a lot of countries. Only when countries where they have other sources of energy like hydroelectric or they have nuclear energy, they can actually produce hydrogen through the what you call that, electrolysis itself, which is easier than here lah. Here they do produce hydrogen in the past to make rocket fuel. I don't think it's so much popular here. You use electrolysis better. Straight water can turn into hydrogen gas and oxygen gas, which is very useful for both. All right. So generally, make ammonia. Yes, ammonia you must know, because under chapter ammonia, you need to know that ammonia are used to make fertilizer, ammonium nitrate, ammonium chloride, ammonium sulfate are fertilizer. Also can be used to make margarine. Okay, so there are three of them. 1, 2 is here, third one is here. All right, let's move on. Okay, let's look at this one here. This is a very interesting question. Question kind of like that one. This is compound after alkene react with bromine. Oh man, this is not highlighted. Wait. Alkene react with bromine. So it does produce bromine here and here. So I must look for the carbon. I don't care about bromine, but I care about position of bromine. So if my bromine is here, I highlight or I draw circle on the carbon. These two are the carbon that has a carbon-carbon double bond. Because bromine can only attach to the two carbon that was a double bond between them. So if I know my bromine is here, my first carbon is here. Second bromine is here, carbon is here. So answer should be double bond here. Look around. And by the way, this is the T structure. Do you realize the T structure like that? I use another color. T structure like that. You see that? T structure. The carbon itself is a branch here, T structure. So cannot be A and B already. Cannot be this, cannot be this. They are straight. So it's either C or D. Then look carefully at the double bond. The carbon, one of the carbon here, the side. Do you know why not D? You count the carbon. 1, 2, 3, 4, 5. I cannot increase my carbon. My carbon was 4 wrong. Look carefully. 1, 2, 3, 4. So answer is C. It doesn't matter you put it, the double put on left or right, because this molecule and this molecule is the same. All right. Let's see whether I can flip it or not. Let me just try. I know double bond seems to be on the other side, right? But it's the same. Let me try. Hey, what's so big? Oh man, I'm supposed to cut this one. Yeah, let me try. See if I can flip it. Hey, cannot. I want to flip it the other way around. Did they flip? Yeah, flip, but oopsie. Yeah, looks like this. You see that? The carbon doesn't look very nice, but it's here. So if I flip this molecule, left and right flip, it turns to this. It's exactly the same, huh? Just that the carbon is opposite direction. So you realize I flip this thing, look from the back, it's like this. It is still on this side. Do you realize that? It's still on this side. And that's identical to our structure. Okay? It doesn't matter left or right when they're symmetrical, because this one is look like when you look from the back. You look from the back, it's like that. It's still these two carbon. Isn't these two carbon same as the position of these two carbon here? I remove the green. Is the same as these two carbon here? Are you with me? So always flip and look the other way around. This one is obviously wrong because of 5 carbon. It's not even the same one. Okay, so this one. Let's look at this. Let me see how much more. Okay, good. Can. Okay, finish whole thing. Okay, look at what kind of reaction do we have here. There are 2 different reactions. Alkene can undergo. The first one is what? Reaction 1 is double bond becomes single bond, right? Obviously, it's addition reaction. And what is the condition is? Okay, do it at my double bond. Turn to single bond, right? What do I add? I add hydrogen, right? So what's my condition for this reaction? This reaction obviously is hydrogenation. So in my working, I would like scribble like hydrogenation. So I know the condition is 150 degrees C and nickel catalyst. Now, if you don't remember now, it is fine, but you try to remember it. Okay, memorize it properly later on. Okay, 150 degrees C and nickel catalyst. Next one. Structure formula of this one. This one reaction is what? It's not bromination. It's not addition polymerization. 300 degrees, 60 atm is called hydration. Hydration is very simple. I just need to add the what? Hydrogen and oxygen, right? So I'm going to do a simple way. I'm going to cut and paste this one. Okay, I'm going to put it here. Hey, why did we give me like that? Irritating. Wait, give me a second. This one. Yeah, oh, this one. Okay, look carefully. I'm going to draw X now. X is actually the same as the top one, except that the hydrogen is slightly different, right? Slightly different. So I must remove the hydrogen here and change to an O and H. So I change to an O and H. That's all I need. Okay? Change the O, then dash H. You can put a dash downward also can. I think to be neat, I will do it the other way. I don't do it sideways, I do it downward. Okay, let me move a little bit up for this one. Okay, my catalyst move now. I draw downward like that. It's correct. Okay, this will be neater. Dash O dash H, hydration. It's okay? Good. The reagent needed to form 2-dichlorobutane to form from butene. Look carefully. Butene form butane, but there's a chloro-BCl. So what's the reagent? What's the reagent? Answer is chlorine gas. Okay, chlorine gas. You bubble the chlorine into the butene will convert, or they mix them together, they will become 1,2-dichlorobutane. Okay, let me check the physical state of butene. Just wonder what physical state it is. Boiling point of butene. Oh, butene is still a gas. If it's a gas, how does it work? Let me think. This is a strange question. Let me think. It cannot be a chlorine gas and butene be that. Do they react? Usually, maybe the question was set in such a way that they do not really emphasize on that. You see, when you have chlorine gas is usually bubbled into alkene. Yeah, and then you will actually form the dichloro. But if the alkene is a gas, then it's the alkene. That means the butene actually is the one that is bubbled into chlorine. But you don't get liquid chlorine also. Liquid chlorine is very low. Let me check. What's the boiling point of liquid chlorine? Okay. Oh, it's even negative. It's even lower than that. Yeah, negative. Yeah. So basically, because the reagent is called chlorine, but I think it may not be a gaseous form. Can it be aqueous form? Let me think. Aqueous chlorine is too weak. Just a bromine. Remember, you don't use aqueous bromine. You use what? You use a liquid bromine. Remember? Yeah, liquid bromine. Yeah. So it could be aqueous chlorine. It could be aqueous chlorine, but it must be very saturated in chlorine. But unfortunately, chlorine is not that very soluble in water. Yeah. So basically, anyway, the answer should be just chlorine. Yeah. I try not to use a chlorine gas because chlorine gas, if you know the detail, chlorine gas and alkene, or both are gases, I'm not sure whether how they react. But that's not in your syllabus, no, don't worry too much. So the reagent is chlorine because to form 1,2-dichloro, instead of 1,2-dibromo, you need the chlorine. Okay? Right. Let's see what they say. They say chlorine gas, very interesting. I'm not sure whether the chlorine gas can react because both are gases. They did not consider bromine, they did not consider butene as a gas yet. But I checked the internet, butene is a gas, unfortunately. Okay. Boiling point is about 0.8 to 3.7. So above 3.7 is confirmed a gas. Chlorine is a gas. No, bromine is butene is a gas. So butene is a gas. Gas in gas reaction, I'm not sure how they react in this case because usually what is it's a liquid. Yeah. So don't worry too much about that. Okay. So you can always say, okay, assuming that you don't know what is this, assuming you do not know. In fact, teachers also don't remember what physical state it is. You can always say if they are to describe, you can just say bubble the chlorine gas into the into the butene. Okay, the butene liquid butene. Okay, yeah. All right. Let me see. These are all okay. The rest. You see, they draw below also igniter, but you draw at the side, nothing wrong. You draw on this side also nothing wrong. You can put an O here, attach the O, then attach H side. Wait, nothing wrong. As long as one side is H, one side OH. But the OH cannot be at the side here. I cannot with this carbon. I repeat here. I cannot draw OH here. Cannot, because it will be this carbon. Since it's a two carbon in the center, the OH can be on either one, but not at the side. Not possible at the side. Okay. Okay, good. Okay, let's go to isomer. So this one you can just look through yourself, the question. I think you have to do it later, but let's go through one more thing, isomer. Okay, we'll end with this isomer. Now, what's isomer? Okay, where does it go to? Sorry. Okay, let's highlight this definition. You need to know. Isomers are compounds of the same molecular formula, but different structural formula. Some schools will teach you to name all the funny isomers, but most schools do not. But then again, at A level, you need to know. That's why some schools teach you a bit more. All right. What do you need to know is that you must know how to draw the different isomer. Draw. Naming is good to know, but drawing is a must. So isomer may have different arrangement of atoms or position of functional group. So in other words, for example, look at this. This is C4H10. C4H10. First, they must equal first. The molecular formula not equal, no need to do already. I repeat, molecular formula must be the same. If not, no need to do already. There are no isomer anymore. So if you draw you two molecule and a molecule of different number of atoms, then they can never be an isomer. Isomer must have same number of atoms, but different structural formula, different structural arrangement of atoms. So look carefully here. I have a single straight chain. They call it straight chain. One line. But this one has a T junction. It's a branch. Okay, so the first one is called straight chain. Second one called branch. Okay, take note of this. Straight chain, one straight line, a branch. You see that? A T junction, a branch. So a branch alkane will be an alkane with a side branch. And this is a branch. Okay? The branch is usually an alkyl group. Alkyl group. Alkyl is another homolog series. Okay, but you don't need to cite too much detail. Just need to know that it's down here, application here. The branch can be a CH3, C1, H2 times 1 plus 1 is 3, CH3, or could be C2, H5. So the common branch you need to know is this one, CH3, C2H5. All right, seldom go beyond that. So the first one is called methyl. You need to know? Yes, they need to know. Unfortunately, not negative, it's a dash, it's a bond. Yeah, thanks for asking. It's not a negative, it's a dash. That means methyl, ethyl, these are not existing by itself. It is a part of a molecule. Like in this case, you see that? A dash and a CH3 here. CH3 plus a dash, a branch. Is it okay? All right, let's move on. Okay, so let's look at this branching here, different kind of branching. But don't worry, I teach you a simple way to look at it later on. Now, let's look at this. Our eyes must focus on only the carbon and not the hydrogen. Don't worry about hydrogen. So I have a carbon, 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 single bond, double bond. Here is carbon, carbon, double bond, carbon, carbon, all the rest are single bond. And this one is double bond, carbon, carbon, single bond, single bond. So to draw simple like this, look at this. I only draw carbon. Can you see that? 4 carbon in a straight chain, double bond in between first and 2 carbon. 1 and 2 carbon. Second one is 4 carbon in a straight chain, but this carbon 1, 2, 3, 4, this carbon 1, 2, 3, 4. Because it's on the carbon 2, that's why it's bu2 in and bu1 in. Can you see that? Highlight 2, bu2 in, 1, bu1 in. The name is slightly different because it tells you the position of the functional group of alkene. So bu1 in means the double bond is on the carbon number 1. You use a small number. You can say number 1 and number 2, but I won't say 2 because 2 could be 2 and 3. So you always use a smaller number, which is 1, because 1 and 2 means 1. 2 and 3 means 2. Is that 3 and 4? There's no 3 and 4 because if it's 3 and 4 like this, then you could just draw the way. You can put the 1 on this side, renumber it. You always number the carbon from the functional group. Okay? So I draw you another one. What I mean is this. If I have 1, 2, 3, like that, then what is this? Do you realize this is identical to the first one? I can call this 1, 2, 3, 4 and label it the other way around. Repeat. So you realize that whether is it joined to the first 2 carbon or joined to the last 2 carbon, they are identical because I also can call it from the other side, still 1. The numbering is not fixed one. The numbering always start calling the number from the number always start from the functional group side. Functional group side. Okay? Now look at this. How do I number this thing? I erase this first. This is called carbon number 1, 2, 3, a straight chain. And then the branch is on number 2. So it looks like this, like that. So 1, 2, 3, and the branch is there. And this branch is called methyl branch. So it's 2-methyl propene. Propene is here. Do I need to put prop 1 in? Do you realize it doesn't matter on which side it goes? It's always prop 1 in one. There's no such thing as prop 2 in. I repeat. Propene has 3 carbon. Whether it's on the left side or right side, it still start counting from 1 on the side which the double bond is. So there's only prop 1 in. So there's no need to put prop in. You just simply put what? Propene. It's different when you have a butene. Okay, that is slightly different. Okay. In this case down here, do you realize that my branch is here? My function group is here. Yeah. So it's 2-methyl propene. Okay. All right. So since actually they cover very little in the textbook, I mean in the textbook or even here, they cover very little, but you need to know how to rearrange the atoms. I'll give you an example. Okay, let me use the alkane as example. Okay, a few more minutes, alkane like that. I get a C5H12. 5. So this is called pentane, right? Now, there's no way to arrange there's no special functional group. So the only things arranged is the position of the branch, whatever. So now, since 5 is the only one you have, this is called pentane. So I draw the 4 carbon in a straight chain. I can draw the functional group here. See that? I draw a functional group at the bottom. So this is called what? 2-methyl butane. Why? Because carbon 1, carbon 2, right? 2-methyl butane. You see that? 2-methyl butane. Even if you join to this side, it's still 2-methyl butane. Because I count from the other side. Okay, let me just duplicate this one. Imagine I draw from the other side. I will still count, not from left, not from right anymore. I count from left. 1, 2, 3, 4. So these both are still called 2-methyl butane. Regardless whether the carbon is on top, below, it's still 2-methyl butane. Is it okay? 2 means the position of the branch, methyl branch. Okay. Third one, I cannot, no matter what I put, I also cannot. If I put at the corner, it becomes the first one again. What do I mean? You see, if I draw like that, this is the what I draw. Okay, I use dot to draw easier lah. The first one is like that. 1, 2, 3, 4, 5. Second one is 1, 2, 3, 4, and here. This one is 1, 2, 3, 4, and here. Am I right? Whether I draw on top, below, it doesn't matter. They're all identical. Okay? Now, what happens if I draw like that? What happens if I draw like that? 1, 2, 3, 4, down. Or 1, 2, 3, 4, down. Or 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Do you realize all these are same as the first one? I just bend the structure a bit. So all these are all under the same category. All these are same as this, equivalent to this. Because why? It's still a straight chain. You see, 1, 2, 3, 4, 5. You count down. The molecule bend, by bending the molecule, I cannot say it's another molecule. They're all identicals actually. They're much more than that. I'll show you another one now. Like that. Like that. Okay? Or can be like that. Do you realize every one of these are straight chain? As long as you have one single path, as long as there are 2 ends to a path, 2 ends only, that is a straight chain. Can? See, look at this straight chain. Follow my pen. Do you see it's a straight chain? Okay, there's no now. As long as you draw in one, you can use one stroke of pen to draw that. Means all these are straight chain actually. In reality, no molecules are straight. I repeat, in reality, no molecules are straight. They are actually not straight. They are curved and bent and everywhere. Is okay? So all these are same. Likewise for this, I show you the difference. Do you realize that I have 1, 2, 3, 4? My straight chain is here. Straight chain is here. My straight chain is here. See that? The branch is still number 2. No different. All right, or I can draw this. This is identical to this. I can draw this. And this still identical to this. Still identical to all this. They're all same. How do I draw a straight chain? See that? I may be bending, but I did not branch out. If I don't branch out, that means one end to their end is joined together like that, a straight chain. It can be this side also, the longer straight chain. Is it okay? So I would say that all this are same, identical. And then all these are identical. So a lot of time people make mistake. They didn't realize that all these are one single chain only. So how do I know it's a straight chain? I only know that there's two ends, one end to the other end. It start from one side to the other side. It start from one side to the other side, one end to the other end. There are two ends to it. It's always a straight chain. A single branch has three endings, one ending, two ending, three ending. The longest one I call a straight chain. This is a branch. Longer I call straight chain, this is a branch. This one is the same thing. One end to the other end, this is a branch. One end to the end, this is a branch. All these are identical. So what's the last but not the same one? Is this one. Sorry, I think I draw too many. Wait, let me check. 1, 2, 3. Okay, sorry, 3 carbon and carbon on top, carbon below. Look at this. This is a T branch across. So this is totally new. And this is called 1, 2, 3. This is called 2,2 dimethyl. Why 2 dimethyl? Because there are 2 methyl branch. And this is propane. So let me draw the center. Center is 1 propane. Then there's a branch on top, methyl and methyl. So propane is the straight one. See that? And 2 methyl, dimethyl, because 1 methyl, 2 methyl joined to the carbon 2. So it's 2,2 dimethyl propane. Okay? And how does it look like in my simplified diagram? Is like this. Two dimethyl propane. It's okay? All right, I will send this to you. All right. Anyway, just a little bit, just give me a few minutes, we're done already. So the difference between saturated and unsaturated, difference. So just remember, saturated means what? Carbon-carbon, single bond. Only carbon-carbon, single bonds. Unsaturated has carbon-carbon, at least one carbon-carbon double bond. And of course, aqueous bromine can be used to test between alkene and alkane. Aqueous bromine remains brown when mixed with alkane, decolorized when mixed with alkene. It's important. Now take note, we're not talking about liquid bromine anymore. We're talking about aqueous bromine. Aqueous bromine is also red-brown. This one's red, sorry, I must add one more. Okay, add one more red-brown. Aqueous bromine is not exactly brown, not a nice brown, but more of a maroon kind of brown, reddish kind of brown. Lighter than liquid bromine, but it's still red-brown. So, how do I use aqueous bromine to test? I'm not using liquid. Liquid is too much bromine. You cannot decolor. You may not decolorize totally, right, for liquid. But aqueous bromine red brown, it decolorize quite easily with alkene. So how to distinguish between alkene, ethene, ethane? This is a typical question. Pay attention to this exam question. Describe a chemical test between ethene and ethane. Explain answer with help of equation. So look at this. The equation is ethene's equation because ethane has no reaction. So you bubble a sample of ethane into down here is aqueous bromine. Sorry, I think it's aqueous bromine. Why do they use this? Sorry, change this to aqueous bromine. Okay. Liquid bromine, when you want to form dibromo, the reaction is a liquid bromine. Other than that, you use aqueous bromine. Okay. It's not totally wrong, but usually we use aqueous bromine. Let me just check the textbook. It's bromine, yeah. Okay, it should be aqueous bromine, I believe. Because aqueous bromine will be the one that decolorize rapidly. Here you are. Okay, I'll show you. Look at my screen. As for unsaturation, you use aqueous bromine. All right. Yeah, they say brown. So interesting. Red, brown, aqueous bromine, brown. Okay, textbook say brown, so okay, can accept brown also lah. But usually in school we teach them red, brown. Bromine is red, brown, not exactly brown. Iodine, aqueous iodine is brown. Yeah. So you listen to teacher, what teacher say to you. Yeah. We used to say red, brown all along. So what happens is that the bromine doesn't decolorize, but if it's alkene, the bromine will decolorize rapidly. Is it okay? Yeah. So the word aqueous. I'll use the aqueous actually. All right. So you see now they say red brown. That's so interesting. At one moment you say brown, red brown. It's red brown. The actual real color is red brown, not exactly brown. Brown, in case you thought it's brown, brown is like that. You see my coffee? This is brown. Yeah. Red brown is a bit reddish kind of brown. Yeah. Slight tints of red. So when alkene bubbles through because you're talking ethane, right? So you must answer specifically ethane or ethene, not alkene. So ethene will decolorize the here. I highlight in blue, very important sentence. Red brown aqueous bromine is decolorized when ethene bubbles through. Okay. Aqueous bromine is decolorized. But ethane does not react with the bromine, aqueous bromine. Like this book. Do you know this book is actually written by the same author that write textbook, but somehow they are not very consistent in the word. I don't know why. Let's be consistent. Aqueous bromine. Yeah. So this is a reaction. Okay. So just now we have done the vegetable oil already. Done already. Just need to emphasize the one word called polyunsaturated. That's all. So the alkene ethane test, okay? Just mention about bubble the gas through aqueous bromine. Ethane will not decolorize the bromine, while ethene will decolorize the reddish brown bromine. That's all. Okay, we talk about vegetable oil. The two kind of oil, basically just need to know there's a saturated and unsaturated. Yeah. And saturated means only single bond. Unsaturated contains double bond. Simple, right? The word saturated means single bond. Carbon, carbon, single bond. Unsaturated means contain carbon, carbon, double bond. Let me go outside. Okay. Now, polyunsaturated, I defined for you just now already. Polyunsaturated means they contain more than one carbon, carbon, double bond. This is another definition you want to know. They say that, for example, vegetable oil is polyunsaturated. All right, polyunsaturated. Explain the term polyunsaturated using vegetable oil. You must say that vegetable oil is polyunsaturated because it contains more than one carbon, carbon, double bond. For example, this one, double bond is here, double bond is here. As long more than one is called polyunsaturated. Saturated is all single bond. This is mono unsaturated, means one double bond. Usually we don't talk about mono. Mono is one. This is poly. So when you have many, how many double bond you have is how many hydrogen you need to saturate it. For example, in this case, if this is a full molecule, 2 double bond here, means I need 2 H2. 1 H2 here, 1 H2 here. The number of mole of H2 depends on what? Depends on number of double bond, which I went through just now already. Okay, just remember this part. The number of carbon-carbon double bond will determine the number of molecules of hydrogen needed to add across it. And that will be one of the calculation questions you see in the MCQ. Okay, good. I think we are done already. Yeah. So, yeah, see, unsaturated. What do you mean by unsaturated? It simply means the fat contains more than one carbon-carbon double bond. All right, so I think we are done for today for these questions. Take note of especially this one. I think this one is not well written. Change the liquid to all the aqueous, right? The red brown is correct. Red brown bromine is correct. Yeah, so maybe the textbook need to change. Again, you ask the teacher, if the teacher explain to you, they say brown, then ask, isn't it red brown? Brown is more for iodine, equals iodine. Yeah. Okay. Right, I will stop my recording here.